Okay, so today we're going to just do more practice with disk and washer method. We're going to be working on page 15 and 16 in our packet. I'm going to try to work through the few problems with you, make sure that we're good with the foundational steps, setting up the problem, and then we can try some of the problems on our own. But I'll still kind of guide us through the steps, make sure that we're comfortable with each of them. Whatever we don't finish, we won't finish for homework, but I think we should get through this 8 problems on the worksheet. We should get through 6 of them, and then the last 2 you guys can finish up and show me for as part of tomorrow's homework. Tomorrow's our last topic. We have a volume by cross section. If we feel good about disk and washer method, then cross section. All it means is that right now, all of our objects, if we were to slice it open, they're all going to be different variations of circles, right? But what if we had volume that if you were to slice it open, you have different shapes like triangles or rectangles or trapezoids or semicircles. And the fact that we're rotating around an axis is what's causing all that circular shape. But volume by cross section, if we want to build different bases like triangle or semicircle or slices of semicircles from one end to the other, it's going to end up looking really strange. But we never have to worry about being able to decipher what the picture looks like. We just have to be able to pull the information to put it into the formula. So the way we pull the information is going to be very similar from what we did with area, with this method, with washer method. So tomorrow will just kind of feel like a slight extension from what we've been doing, but it won't feel like completely radically new. It just feels like just a different, slight variation of what we've been doing. And then we can begin our quiz review. So Wednesday we'll do quiz review. Thursday, Friday we'll do a little bit, but I do want to start our AP review with anti-derivative word problems, and then after break we'll have another full day to review, and then your quiz will be next Friday. All right. Okay, so let's go to page 15. So it says a washer method practice problems, but there's a mixture of washer and this method. We need to make sure that we can memorize these formulas. So on page 20, you're going to see a list of formulas. It looks like a lot, but there's just variations of basically just like 3 major formulas. We have area, which is top minus bottom or right minus left. There's no squared within our expression. We just find that height difference or the length difference of our rectangle, and that's it. For this method is if we're rotating around an axis, but there's no gap, so it's just going to be big R squared. And then washer method is if there's a gap, and we have to subtract out an additional radius, so it's going to be big R squared minus little r squared. And then tomorrow we'll finish up with cross section, different shapes besides circles for our cross section. Okay, so page 15. Let me just highlight real quick as in terms of so we can make sure that we can distinguish the difference between washer and this method. And it's really coming down to a visual standpoint. So let's say this is my, you don't have to write any of this down. You can just kind of watch along here. If I had a vertical axis here, and then my shaded region looked like this. Okay, which one will this be? Disk or washer method? This, right? You see there's no gap at all. It's a flat surface. That dotted line is right up against that straight horizontal or flat surface of a shaded region. So this is going to be this method. Okay, what if I had an axis here? And it's touching. What do you think this one is? Washer method. I know a lot of students feel like, oh, if it's touching, that's good enough for this. That's not quite correct. It is touching, but there's all this gap, right? You see this gap here. That gap is enough for us to know to subtract something out. There's going to be, okay. And finally, let me do one. How about this one here? It's washer, right? This one is easier to spot. There's not even touching, so there's obviously a gap. So I think students feel pretty good about this method. Well, at least this is, I think, the easiest one to students don't mess up with this. That's usually not an issue. This method, I think students are pretty good here. I think this is where we run into some trouble. Students feel like, oh, that is enough for this method to stand, but that's not true. If it's touching, but if it's along a curved surface, that's going to be washer method, right? So just be careful about this scenario. Touching at between the dotted line and the shaded region is not enough for this method. It's got to be up against a flat surface like this one. Right? Make sure we can distinguish between these two here. Okay, so let's look at number one here. We're gonna have our shaded region. We have root x minus 1. That's the radical function here. We got the horizontal line, y equals 1, that's up here, and then the y-axis here. So I'm going to shade this in. Rotating about the line y equals -3. This one already drew the line for us, so we can just use it. This method or washer method? Washer, right? There's a complete gap. What if the dotted line was up here at y equals -1? Still washer, right? There's only two places where this graph can support this method is if it's up against the y-axis like so, or if it's right at y equals 1, right? If you don't see a flat surface, there's no, we don't have an opportunity to do this method. Okay, so we're going to do 2 radius. Your axis is horizontal, so that means your radius will be which direction? Vertical. It's got to be different direction than your axis. So, and we're always extending from the axis out. Okay, we don't have to visualize fully what the graph looks like, but just enough so that we understand this is really the center of the object, because this is going to rotate around that axis. So as long as we know this is the center, we know that the radius will include the center, and that's why our radius always extends from the axis. Okay, so from the axis, you're going to extend to the furthest boundary of your shaded region. Call that big R. And then from your axis to the closer of the two boundaries, that's your little r. Okay, let's build our 2 radius, big R and little r. Okay, top minus bottom. What's the top of big radius sitting on? 1 minus -3. Yeah. So careful with the negatives here. If you see multiple negatives, they're going to change each other's sign, become 1 plus 3. The nice thing about a vertical radius is that our equations don't have to be rewritten or adjusted. We can use whatever form they give us. Okay, small radius. What's the top of little radius sitting on? Root x minus 1. Minus -3. So -1 plus 3 is 2. So root x plus 2. All right, we have our 2 radius ready to go. They're going to go in this integrand portion of our volume formula. But notice everything's in terms of x, so our bounds is also in terms of x. That means we're stacking these circular rings from this side all the way to this side. What's the furthest left x value that you see? 0. What's the furthest right? Oh, the shaded region, though, the shaded region. 4. Now, is this point right here. Now, let's say this graph, the axis was not labeled like this, which you can expect that on the quiz. It won't be labeled. How can we find that this is 4? Yeah, set them equal to each other. Or you can graph the y equals 2 and y equals root x minus 1 and just look for that intersection, use the second trace intersect feature. But I want to show the work here. If I want to do this by hand, I would set 2 or root x minus 1 equal to 1. Bring the root 1 over. Square both sides, I get 4. Our left bound is 0, our right bound is 4. We have our big R, we have our little r ready to put into our volume formula. Big radius squared minus little radius squared. Okay, let's go to our calculator. I'm going to let 4 be inserted into y1, and then I'll let the root x plus 2 under y2. Make sure that you clear that radical before you do the plus 2. We don't want that radical to extend out past the root x. Okay. Second mode, go back to your home screen, Math 9. 0 to 4, we'll do alpha trace, or if you're using the older calculator, it'd be vars, y vars function y1 or y2. If you try to get it into a fraction, it won't change. So you can leave it, your answer, and round it to 3 decimal places, 18.667 cubic units. Pi, sorry, units. Cube. Any questions with 1A? Okay, part B, same shaded region. How was our axis different here? Vertical, yeah. So disk or washer? Yeah, washer still. There's a gap. We need 2 radius. How is our radius going to look different than previously? Horizontal. Yeah, horizontal. And we have 2 of them, right? So so this is, again, this is the center of your circular ring object. So make sure that any radius you build always has to start here and extend out. And extend to the further region, that's going to be the big R. Call it big R of Y. Okay, from the axis of revolution, we can extend to the closer of the 2 boundaries, and that's going to be little r. Okay. What adjustments do we have to make if we see a horizontal radius? We gotta rewrite the equation. Make sure that you don't just swap the x and y. That's not good enough. You have to actually algebraically move things around and actually solve for x. So we have y is equal to root x minus 1. If I just have the right side to be on the left side so that I can just solve for x this way, just visually maybe easier, but we don't have to do that. But what can we do to eventually solve for x? We can do first, do what? Add 1, okay. Next up, square both sides. Okay, we can let that represent that curve. And the y-axis has an equation of what? X equals 0. And then we have axis being x equals -1. If you look at all these equations, they all have a common form, right? X equals, x equals, x equals, and they're all in the proper form for us to pull from and put into our radius equation as we need it. So we'll do r of y. Okay. Big radius, we do right minus left. What's the right endpoint of big radius sitting on? Good. It is the radical, but it's been rewritten. So y plus 1 squared minus, look at the left endpoint. What's the left endpoint of big R sitting on? -1. Careful with the two negatives there. Okay, I'll clean that up later. Big little r. What's the right endpoint of small radius sitting on? The 0. Minus -1. Okay, everything is in terms of y. Our integrand is in terms of y. Our bounds have to be in terms of y as well. We have to identify the lowest and highest y value. What's the lowest y value that you see? -1. What's the highest y value that you see? What's the highest y value? 1. Okay. Now, what if this -1 wasn't shown to us? How would we find this point? Yep, good. So this is where the curve intersects with the y-axis. So anytime a curve touches the y-axis, that's called the y-intercept. So y-intercept always has an x value of 0. So if I insert 0 in for x, y at that point is 0 minus 1, which is -1. Okay, here's my big radius. Minus little radius. Okay, practice entering in our calculator. We'll do have this under y1, have this under y2, and we'll do math 9 from -1 to 1, y sub 1 squared minus y sub 2 squared dx. Okay. Any questions with 1A or 1B? Okay, let's take a look at number 3. Sorry, number 2, part A. We have the graph 3 minus x squared. That's this parabola opening down. The line y equals -2. That's down here. Find the volume of the solid generated when the region is revolved about the line y equals 3. So here's my shaded region. I put the x and y axis here just to give us a frame of reference, but the x and y axis are in the background. It's not going to produce any intersections that we care about. So just ignore the X and Y axis. It's really just the curve and the line that's going to provide any boundary for us. Okay. How is this axis going to look? Horizontal, okay. And is it going to touch the graph? Yes. Yeah, the graph, the y-intercept for the 3 minus x squared is 3, and the dotted line will skim the surface of that parabola. Okay. So what relationship is this? Disk or washer method? Washer, good. It's touching, but we don't see any flat surface here, right? There's all this gap here. It's not like as if it was down here. If it was down here, it'll be this method. Okay. Extend your 2 radius from the axis to the 2 boundaries. Big radius will extend all the way down there. Little radius. Okay. Big radius, top minus bottom. Top is sitting at, what's top of big radius sitting on? 3 minus. Good. We gotta keep track of our 2 negatives here, right? Okay. Top of little r. Starts at where? 3. Minus, what's the bottom of small radius sitting on? Can I do this? Top minus bottom. Okay, what's missing? Parentheses, right? There's multiple terms in my bottom function. If I don't put the parentheses, I'm going to forget to distribute that negative through. That makes a big difference. Negatives. Because the bottom of big radius is sitting at that line y equals -2. Yeah. And then for small radius, top is sitting at the line, the bottom is sitting at the parabola. So 3 minus parentheses 3 minus x squared. Okay, so that big r just cleans up to be 5. Little r just cleans up to be positive x squared. We still need to find our boundaries. So everything's in terms of x, so our bounds is also in terms of x. We want to find the furthest left to the furthest right. We're stacking these circular rings from this side all the way to the other side. How can I find these two intersect? How can I find these two bounds? Set them equal. Or we can go to our calculator and do second trace intersect. I'm going to solve it by hand since this is easy enough for us to do that. So okay, go ahead and try part B. See if we can decipher between this method or washer method. Okay, what do we decide for part B, disk or washer method? This method, okay. All we need is one radius to extend from the dotted line to the shaded region, to the boundary of the shaded region. Then we do top minus bottom. Just one big radius squared, no need to subtract anything else. And the bounds will stay the same. Same shaded region, same orientation. Whenever you're ready, let's go to page 16. Let's see if we can at least get through A and B for number 3. And I'll work alongside you guys as you try these problems. Does anybody still need page 15? Don't forget about your parentheses, especially as your bottom portion will always have multiple terms for this one here. Now, in your calculator, you're going to be closing off a set of parentheses around the x. Make sure that you don't wait until the -2 to close off that parentheses, because the 2 is not inside the natural log. It's natural log of x, and then it's reflected, or it's shifted down -2. So the 2 is not inside the natural log. So I want to make sure that we see that. To find the intersections for our bounds, this is not an easy situation to solve by hand. You got natural log of x, a constant, and x. It's hard to solve that by hand. We're going to go to our calculator. We'll make the calculator find that intersection for us, or find those two intersections for us. So I'm going to go to y1 and y2. Now, when I'm entering y1 and y2, I'm not going to plug in big R and little r. That's something else. I want to actually see what this graph looks like. So I'll let y1 hold, held by that natural log of x minus 2. And this is my y2. Now, when you type in y1, make sure you, again, that you close off your natural log of x before you do a minus 2. Okay, go to Zoom. Zoom 6, it may not be the perfect window for you, but at least you can get your window centered, and then you can decide what you want to do to maybe box off the region that you want to look at. So Zoom 6. Okay, it's a little bit small here. I'm going to do Zoom box, Zoom 1. Create a box around my region there. I'm going to put my cursor where I expect the upper corner of my box to be, upper left corner, hit enter. And then you're going to drag and drop until you see the box in front of you. Enter. A little better. I'll do a second trace intersect on the board there. Second trace intersect. Second trace 5. I'm going to pick points close to the intersection. Enter, enter. So 3.146. I'm going to also write down the y value. I'm not going to need the y value right now, but the y value will be helpful when we get to part B, when we have a different axis of revolution. Okay, I'll do a second trace intersect again. This time I'm picking points closer to my further left intersection. So hit enter, enter. Get 0.158 and negative 3.841. Okay, everything I need is in front of me. X sub 1 and X sub 2, these are my bounds for okay, part B. What's different about part B? Vertical axis. Big R of Y. Little R of Y. Anytime we see a horizontal radius, that means we have to do what? Yeah. Solve for X. Yeah. Algebraically move things around, solve for X. So let me do the linear graph first. This is the y equals x minus 4. So I'll make that x minus 4 on the left side here. Solve for x. It's my linear graph. Let me highlight that. Okay, the curved graph, that's the y equals natural log of x minus 2. Natural log of x minus 2 is equal to y. Okay, so if I want to solve for x, what would you do first? Add 2. I want to solve for x. X is stuck inside that natural log, so what can we do? Yeah, raise both sides. E is the base. E and natural log will cancel each other out. My graph in green. Okay, everything's in front of me here. My bounds, I can use the y values there. Let's build our 2 radius, big R. Okay, right minus left, what's the right endpoint of my big radius sitting on? Good, the linear graph. Minus, what's the left endpoint of big radius sitting on? Right minus left for little r. Right endpoint of little radius is sitting where? Plus 2. Minus left endpoint of my little radius is at a negative 1. Okay. Y values. I'm going to clean up my big radius and little radius. Y plus 5, quantity squared. Enter in your calculator, use x's when you put your y1 and y2. Okay, any questions? Okay, so for homework, you'll finish number 4, A and B. But I'm going to be checking both pages 15 and 16 when I walk around tomorrow. I'll send you guys a reminder this afternoon and also a link to the worksheet key so you can check your answers for number 4. Okay, bye, can you mute your phones? Thanks.
Right, let me show you. You may have U0 instead. That's what you did for one of your bounds. Let's see.
Because that's the lowest Y value. Lowest Y value is that. That might be it. Okay.
Can you show me how you do the Zoom thing again?
Yeah.
How to make the box?
Right, so you do zoom.
Yeah.
Yeah, zoom one. And then you're gonna move the cursor to where you expect the upper left corner of your box to be. So maybe I'll set that to enter. You're gonna draw the box out first before you hit enter again. Now it should be.
I was so confused and then I got lost. I was like, oh.
Okay, yeah, let me know if you have questions.
So you just like go over to where,
Okay, yeah, okay, so,
How do you-
right, so if you want to find the intersection, you're gonna make the calculator do it for you. So you do second trace intersects.
Okay.
Second trace.
Okay. So hit 5, or you can go down the side either way. Okay, and then let's say you want to figure out what this point is first, okay? So it's asking for first curve, so it just wants to know what two graphs you want to pick. So I'm gonna pick this graph first, hit enter. Now going to the other cursor, hit enter. So now these 2 points are close to the intersection. So it's gonna find the intersection for you. Guess question mark, hit enter a third time. It's gonna find that intersection.
okay.
And then you do second trace again. And now you can pick points closer to this intersection and it'll find that for you.